So in this video we'll study how to formulate the finite element equations for plane stress plane strain problems. We have seen in the previous video that for plane stress and plane strain the expression for strain energy are same, and the only difference is in the D matrix. So the same program runs for both plane stress and plane strain cases, only you have to appropriately select the D matrix. So suppose you take this body which is an adequately constrained 2D elastic solid subjected to in-plane loads. So these are the in-plane concentrated loads, and this is an in-plane surface traction or surface force, and this is load per unit area of the surface. Also you can specify it as load per unit length of the surface. So you have to first discretize the whole structure using these two planes, plane stress, plane strain 2D elements, and we have only shown a partial discretization here. Now if you take out one element, so suppose this is an element, for our convenience we have taken it as a 3-node element, but the following analysis which we are going to show here is not limited to 3-node elements. So it is also valid for rectangular elements or quadrilateral elements. So here there are here we have shown 3 nodes because it's a triangular element. So it has got 6 degrees of freedom. So 1 u degree of freedom and 1 x degree of freedom and 1 y degree of freedom. That means the displacement in x and displacement in y, displacement in x and displacement in y, displacement in x and displacement in y. So this DAE is an infinitesimal area within the element, and within the element ux and uy varies. Within the element ux and uy varies, so we call it uxe. That means similarly there is one uye. So this is uxe and this is uye. This is a function of x and y within the element, and on this node there is a surface traction vector. This vector has two components. One is in the x direction which we call txe, and one in the y direction which we call tye. And this txe and tye, they are also functions of x and y, but they are defined only on the surface 2, 3. For some other element it may be defined on surface on edge 1, 2 or on edge 1, 3. So now if we proceed, so first we have to find out the potential energy expression, and for potential energy first strain energy is required. So strain energy is this, be it plane stress or plane strain, and sigma E is defined as D into epsilon E, where D is the stress strain matrix and epsilon E is this, which is already known to you. So Txe, Tye, they are surface traction. Here we are considering it as force per unit area, and Bxe, Bye is body force per unit volume. So body force means gravity is a body force, and here for this, if you consider this as x-axis and the vertical one as y-axis, then the body force can be, the gravity as a body force can be expressed like this. So this is, gravity is an example of body force. So now the potential energy expression pi is strain energy minus potential of loads, and this is the strain energy expression, and this is potential of load, that is uxe into txe and uye tye, and on sorry, here, and integration has to be performed on the edge S23, that is on this the integration has to be performed, and this is DSE or DS23E, whatever you say, DS23E. So so this has to be integrated on S23E, this has to be integrated on this, and so this thickness we are multiplying, so thickness multiplied by this gives you, so if this is the length variable, then T into this is on the surface area. So if you express it as force, traction force per unit area, then you have to include T, and if you want to express it as surface force per unit length, then you need not consider T. So this is the body force, and the body force is on volume, so T dAE is the volume of the element, of the infinitesimal element corresponding to this dAE. So T into dAE is the volume, and this is the potential of load due to the body force. So, and this is actually the potential of load due to the nodal displacements and nodal forces. So there are 6 displacements, 6 degrees of freedom, and displacements corresponding to those 6 degrees of freedom, and these are the corresponding forces along those degrees of freedom. But this may not be considered this is not of much importance, because suppose you consider this case where there at this node is surrounded by 4 elements I, J, K, L. So on this node, now if you consider the equilibrium of this node, so this 4 elements, so at this ith element at this node there are these 2 forces, at jth node there are these 2 forces, for jth element at this same node these are the forces on the element, and for kth element these are the forces at this node on this element, and these are the force for the lth element at this node on this element, acting on this element. So if you now consider this node, so the opposite forces will act on the node, and if two external forces Px and Py act on this node, then this is the equilibrium diagram. So this is the equilibrium diagram. Now if the displacement here is ux and uy, then the potential of load due to all this is the potential of load due to at this node, the potential of load due to all these forces is this. So if you consider this term, and assemble over all elements, and if at this node there is no external force, then this would become 0, because the summation of all these forces is 0 if there is no external force, and if there is external force, then sum of this is the external force Px and sum of this is the external force Py. So if there is an external force at that node, then after assembly you have to put these external forces at the appropriate degrees of freedom. So just compare it with what we studied for bar elements. Here there are 2 degrees of freedom, but in bar element per node there are single degree of freedom. So it is better to understand this thing from the study of bar elements. So now if you proceed, just uxe on UYE, that is the displacement in the x direction within the element and displacement in the y direction within the element, is the, so UXE would be N1 UX1, N2 UX2, N3 UX3, and UI is N1 UY1, N2 UY2, and N3 UY3. That means we are getting this UX from the nodal x displacements by interpolating the nodal x displacements. So these are the interpolating functions. N1, N2, N3 are the interpolating functions. So what they are doing, they are interpolating the nodal values to get the value at a given point within the element. So similarly, this is for UI. Here N1 UY1. So for UI, the y displacements at the nodes are interpolated, and this matrix we call the shape function matrix N. And you know that this is the strain within the element is defined like this. So if UXE is N1 UX1 plus N2 UX2 plus N3 UX3, then del UX del UY del UX element del X of UXE is dn1 dx ux1 plus dn2 dx ux2 plus dn3 dx ux3. Similarly, this del uy del y is dn1 dy uy1, dn2 dy uy2, and dn3 dy uy3. And for the shear strain, it is del ux del y. So this into ux1, but del uy del x. So this into this. So this is the strain displacement matrix, or simply the B matrix. So now the strain energy can be written as, here if we call this nodal displacement vector, that is ux1 uy1 ux2 uy2 ux3 uy3. So for triangular element there are 6 degrees of freedom, but if you do it for rectangular or quadrilateral elements, then the number will increase, but the procedure remains the same. So here now you replace epsilon E by B U. That means U transpose B transpose, and U does not depend on dAE. So you can take this U out of the integral, and at the same time this U, which is coming from this epsilon E, B U, out of the integral. So this is your stiffness matrix, as you know. This is your stiffness matrix, and here the second term. So just ux uy is n into u. So ux uy transpose is u transpose n transpose. So u is taken out of the integral, and this is this term. Similarly, the body force term becomes this. Only difference between this is the surface force is integrated over the surface, and maybe we missed some notations, some symbols here. So here it's okay. Oh, here also you have to now it looks okay. Let us save it. So the only difference between the surface force and the body force is, here the integration has to be done on the surface, and here the integration has to be done on area. or on volume. T ds23 is infinitesimal surface area and this is infinitesimal volume, and this is ds23e is just the length part, dae is the area part. So again I repeatedly tell you that when you are specifying txe and tye as force per unit area, then this t has to be there and this is a length variable, and when you specify bxe bye as force per unit volume, then T has to be there and this is unit and this is infinitesimal area. But what you could have done is you could have specified it like Tx multiplied by T, Ty E multiplied by T, then it would have become force per unit length, and this would have become, if you include T here, this would become force per unit, this is force per unit area, force per unit area, and this is area. So please keep this in mind, and this is the finite element equation. So this B is 3 into 6 matrix, so B transpose is 6 into 3, this D is 3 into 3, and this P is 3 into 6, and here this is 6 into 2, 2 into 1, so ultimately 6 into 1, so here 6 into 2, 2 into 1, 6 into 1. Again it is for a triangular element. If you consider quadrilateral elements, then the 6 has to be replaced by 8, 8, 8, 8, and you get the finite element equations. So next we will start studying constant strain triangle, and we'll learn how to find out the shape function matrix, how to find out the expressions for each one of the shape function, and what is the form of the B matrix, which is the strain displacement matrix. Okay.